solve in order to get the normal stresses, and that kind of says that it's free of shear. Does this make sense to everybody? Yes, sir?
So why don't you use theta, instead of finding 2 theta P1, why do you go all the way around and add that 180 degrees instead of?
Oh yeah, so why don't I, so as you said, why don't I just go from here to here, right? I could do the same thing.
The same thing, it's going to give you.
It is going to give me the same thing, exactly the same thing. So I could do clockwise, I could do counterclockwise, as long as I'm consistent. That's all it matters.
Okay.
Right. So let me do that as you said, very quickly. So now instead of going all the way 180 degrees, I'm going to go here. Let me call it as some 2 theta prime, maybe 2 theta double prime. Now notice I'm going to sigma 2 value, not sigma 1. Okay, so that has to be established at the beginning, at the outset itself. Which is sigma 1, which is sigma 2. The larger signed value is sigma 1. Okay, so if I go this way, 2 theta double prime is 53.1, so theta double prime is n by 2, CCW from CA, but it is important to realize that I'm going to sigma 2. Okay. X-axis, Y-axis, I'm still going counterclockwise. Okay, so let's call that as X double prime, Y double prime. Once again, the Y-axis is drawn counterclockwise from the X double prime axis in this case. This is theta double prime. And if I draw the state of stress on the plane element, I'm going to have a rectangle similar to this. X double prime, Y double prime. Which stress value am I going to? I'm going to sigma 2, which means that on the X double prime direction, I'm going to have compressive stress. And on the opposite side, I'm going to have tensile stresses because that's the one that's left over. So this is going to be 10 megapascals, 190 megapascals. And what do you know? This is exactly the same creature as this guy. No matter how you go, the moral of the story, no matter how you go, choose something that you're convenient with. Counterclockwise, because we've always been primed to think of counterclockwise as positive. That's the only reason I'm sticking to that. I'm not wedded to it, but it's good to use a consistent set of rules. So typically I go counterclockwise, I draw the element, and for me, it is not important what these axes are called. It is more important as to what the magnitude of the stress is and what the direction of the stress is. That's what decides how things are going to fail. Okay? Any questions on principal stress? Yes, sir. Question.
When we draw the plane state of stress for a principal stress, theta P1 will be sufficient enough to draw the orientation, to draw the ship. If you find theta P1 before theta P2, you don't need to calculate theta P2.
You don't need to. It's 90 degrees plus that.
Yeah, you just do the
Absolutely. But when you're drawing it out, right? So you've got to be careful as to what you're going to be calling as theta P1. In this case, theta P1 is still this angle because I'm going to go to the maximum principal stress. All right. Now I'm going to list out all these strain relations. I'm going to get rid of this particular panel right here, and I'm going to list out all the strain relations. And it's very simplistic because if I see 3 stresses, let's say, sigma xx, sigma yy, sigma cz. We don't have sigma cz in any of our problems because we're assuming a plane state of stress, but just humor me. Let's assume there are 3 of these guys. Okay? Sigma xx is going to cause a strain epsilon xx. So this is epsilon xx due to sigma xx is going to be linear elastic isotropic material. So this is sigma by E, right? Sigma xx divided by E. But we also know if you have a linear elastic model, a material model, Poisson effects ensure that a strain in one direction causes a corresponding negative strain in the other direction. If I have a tensile strain in one direction, compressive strain in the other two orthogonal directions. So I have a sigma yy which is going to cause an epsilon yy. So epsilon xx due to sigma yy is going to be minus nu times epsilon yy, right, based upon the Poisson ratio and experimentally determined as well for linear elastic materials. Epsilon yy is sigma yy by E, so this is nothing but minus nu sigma yy by. Likewise, epsilon xx due to sigma zz. If I have a strain epsilon zz in the z direction, this is going to cause two other strains as a consequence in the y and the x direction. So I'm going to have one contribution minus nu. It's always negative because a strain in one direction causes a complementary strain in the other two directions. Okay, positive or negative depending on which one the first one is. So this is going to be minus nu sigma zz by E. I'm going to get rid of this panel here as well. Okay. And so you see, I don't have a chalk. I have 5 minutes. The great thing about linear elasticity is that the principle of superposition is obeyed, which means I can take a strain and I can add it up bit by bit, and I will get the total strain. You cannot do this for materials that undergo permanent deformation. If it is a plastic deformation, there is no direct corresponding relationship between stress and strain. It's either nonlinear or there is no relationship at all. It is completely empirical. So in this case, the total epsilon xx is xx due to that, due to that, and the last one, xx due to sigma zz. So if I add them all up, you can see that the Young's modulus is a common factor. So epsilon xx is 1 by E sigma xx. Does this make sense to you? It's very elegant in my opinion. And the great news is that shear strain in one direction does not do any harm to shear strains in the other two directions. Okay, because it is more of a shape controlling effect, it's not a volumetric effect. If I try to change this dimension in one direction, the volume is going to change. So strains, principal strains or normal strains typically are volumetric. Shear strains are shape changing elements. So they are dilatory. Okay? So this can be generalized in the following manner. Just bear with me for a few more minutes. Epsilon II is equal to 1 by E, watch this, sigma II minus nu times sigma jj plus sigma kk where I is not the same as j is not the same as k. Makes sense to everybody? I can choose I to be xx, j to be yy, and k to be zz, and I can keep cycling through these possibilities. Okay, and I can write it as sigma jj is equal to sigma epsilon jj is this minus the rest of them. Okay, so you can cycle through. Indices or the subscripts. The indices are the ones that are acting as a subscript. And the shear strains, gamma ij is always tau ij divided by the modulus of rigidity. and experimentally determined that shear strains in one direction does not disturb the nature of the shear strains in any other direction. Okay? And lastly, this is a relationship that one can derive, but I'm just going to write it out. I'm not going to ask any questions on it. E can be related to Poisson's ratio and the modulus of rigidity by the following equation. This is also experimentally proved that these material constants obey these kinds of laws when you're looking at elastic strains. And that being said, because of the fact that I reached this material very late, the strain material, I'm not going to ask the strains, these formulas in the exam. Okay? Just to be fair to everybody. I want you to understand that a strain in one direction has an effect of causing, a normal strain in one direction has an effect of causing a normal strain in the other two orthogonal directions. But shear strains, they don't do anything to the other two directions. Okay? So for the exam, please hang on, I think he has a question, but please hang on. For the exam, you will have all of that, principal stresses, maximum in-plane shear stresses, draw the Mohr circle, draw the orientation, show me the directions, is it clockwise or counterclockwise? Be consistent with your directionality, okay? And questions?
Yeah, so the last part of the last question on the homework is shear with...
I leave it up to you guys. If you want to do the last part of the last problem in the homework, that's completely fine. If you do want to do it, you can assume that the modulus of elasticity is that of steel. One type of steel, there are millions of types of steels. Poisson's ratio is 0.5, and this is 56 gigapascals. If you use the formula, you can find G. If you want, you can do the last part of the last problem of the homework, but I'm not going to ask that material in the exam. Is it fair to everybody? We got to this very late in the semester, but I still want to have an idea of a Mohr circle. I want you to make sure you understand Mohr circle, at least drawing it out. A deeper material will go into failure theories later. Thank you very much. Good luck to all of you.